Hello students, this is Mrs. Zimmers and I am making you an updated video for our topic of inverse trig functions. Most of the videos on my YouTube channel were made a couple years ago during COVID, and perhaps the lessons have been modified a little bit since then, so I thought let's just go ahead and update this one. And I am a little rusty on my video production skills, so I apologize if I go a little bit slow. You can always speed up the rate at which you're watching the video, and feel free to pause anytime, rewind, whatever you need to do to get the notes you need. You can figure out which notes number you're on based on just your notes from class. And this is our second lesson about inverse trig functions. So let me just recap the highlights of the first lesson before we start today's notes. We learned last time that the function y equals inverse sine of x, which is also known as y equals arc sine of x, is the function that is the inverse of the sine function. And so what we're doing is we're inputting a sine ratio, like a ratio of opposite over hypotenuse, some fraction, and we're outputting the angle that would give us that ratio. So input the ratio, or the exact value, whatever you want to call it, output the angle. Now we know if something is going to be a function, it has to pass the vertical line test. So for every input there is exactly one output. But we also know that there are many, many different angles that have the same sine value. And so the inverse sine function, what we learned last time, is that we just restrict it to a certain piece, and then from that piece we get a single answer for the angle. And so for this function, we're going to get answers from quadrant 1 and quadrant 4. And so those answers will be somewhere between negative 90 degrees and 90 degrees if we're using degrees, or between negative pi over 2 radians and pi over 2 radians if we're using radians. Similarly, we have y equals inverse cosine of x, or arc cosine of x, and for its outputs, we want angles from quadrant 1 and quadrant 2. Those would be angles that fall between 0 degrees and 180 degrees, or if you're using radians, between 0 radians and pi radians. And lastly, we learned about y equals inverse tangent of x. And the outputs there are going to be from quadrants 1 and 4. So just like with inverse sine, we're looking for outputs that fall between negative 90 and 90 degrees, or between negative pi over 2 and pi over 2 radians. And yes, there are inverse secant, inverse cosecant, and inverse tangent functions. We're just not going to focus on those in our brief study this time. Okay, so we're going to do a different kind of example today, and you'll notice it looks a little bit more complicated. And so what we have is something going on inside of something else. So we're going to do the inside first, simplify it, and then apply it to the outside. So the inside is inverse sine of 2/3. That means find the angle whose sine is 2/3. Notice that 2/3 is positive, so you want to be in quadrant 1. So draw a reference triangle. And because the sine is 2/3, 2 goes on the opposite, 3 goes on the hypotenuse. Now technically we don't actually need to know what this angle is. I could give it a name. I could call it theta. So this right here is theta. And now our job is to find the cosine of theta. Well, if only we knew the other side of the triangle, we could find the cosine. So what we're going to do is use the Pythagorean theorem. And we have that missing side squared plus 2 squared, that would be 4. Trying to erase, there we go, equals 3 squared. So x squared plus 4 equals 9, so x squared equals 5, so x is square root 5. Okay, so now that we know that, we can find the cosine of the angle without even needing to know the angle. So the cosine of the inverse sine of 2/3 is square root 5 over 3. Okay, let's try another one. let's find the secant of the inverse tangent of negative 15/8. So the inside of that, the inverse tangent of negative 15/8, that means find the angle whose tangent is negative 15/8. And after we do that, we will apply the secant function to it. So inside first, and then outside. So just like we did for number 1, let's draw a reference triangle. And because we have a negative inverse tangent, so where is tangent negative? Tangent's negative in quadrants 2 and 4, but we're limited to just quadrant 4. So let's draw the reference triangle in quadrant 4. And we know tangent is opposite over adjacent. So the angle, if you want to give it a name, this whole thing represents angle, let's call it alpha. So this means this is angle alpha, or if you want to talk about going counterclockwise and getting a negative, that would be angle alpha there. Okay, now using the Pythagorean theorem again to get the missing side, we'll call the missing side r. So we have 8 squared plus negative 15 squared equals r squared. So we have 64 plus 225 equals r squared. So 289 equals r squared, and r is 17. So that worked out nicely. Okay, so we don't need to know alpha, we just now need to find the secant of alpha. So looking at the triangle, the secant is the ratio of hypotenuse over adjacent, that is the reciprocal of cosine. So our answer would be 17/8, 17/8. Okay, let's see what's next. Number 3. Let's just make this more complicated. However, the same principles apply. You have something going on the inside, and you have something going on the outside. Let's figure out the inside first. Okay, now, arctangent 4/3 means an angle whose tangent is 4/3. Let's call that angle alpha. And arccosine 12/13 means an angle whose cosine is 12/13. Let's call that angle beta. So do you notice that what we're looking at here is sine of alpha minus beta? So hopefully that looks familiar. That's one of our difference. We have an identity for that, right? One of our difference identities. And we know that sine of alpha minus beta is going to be sine alpha cosine beta minus cosine alpha sine beta. So we need a reference triangle for alpha and a reference triangle for beta. Let's do that. Going back over here, so the arctangent of 4/3, notice that's a positive 4/3. So we're going to draw a reference triangle in quadrant 1 where tangent is positive. Make the opposite 4, the adjacent 3, and the hypotenuse will be 5. We're familiar with that, 3, 4, 5. If you've forgotten about that, you can use your Pythagorean theorem. And so that's alpha. And do the same thing for beta. So notice that we have a positive value there as well. And cosine is positive also in quadrant 1. So reference triangle for beta in quadrant 1 with adjacent 12 and hypotenuse 13. And using the Pythagorean theorem is going to lead you to 5 again for the missing side. So nice numbers this time. Okay, so we're doing sine alpha. Look at the triangle. Sine alpha is 4/5 times cosine beta. Look at the triangle, 12/13 minus cosine alpha, 3/5 times sine beta, 5/13. And so we get 48 65ths minus 15 65ths, and that's 33 65ths. Not so different from the problems you did a few days ago. It's just that the angles were expressed in a different way. Number 4. Once again, you have something going on the inside and something going on the outside. Let's focus on the inside. Arctangent of -5 means an angle whose tangent is -5. So let's call that angle something. We could call that angle alpha. So really this problem boils down to finding the cosine of 2 alpha. we have identities for that as well. We have 3 of them. Cosine of 2 alpha, let's just choose one of those identities. Let's say cosine 2 alpha equals 2 cosine squared alpha minus 1. Might as well pick one that's has a single exact value in it instead of multiple exact values in it. Okay, so let's go back and make a reference triangle for alpha. Notice that tangent is negative, and so that means we want to use quadrant 4. And tangent being negative 5, well, we could think of negative 5 as the ratio of negative 5 over 1. So let's put negative 5 on the opposite, 1 on the adjacent, and then let's use the Pythagorean theorem to find the other side. So 1 plus 25 equals r squared. So r squared is 26. So r is square root 26. Okay, now let's go back here. We're going to find 2 times cosine squared alpha minus 1. And that means 2 times whatever you get for cosine alpha squared minus 1. So what do we get for cosine alpha? Well, looking back at the triangle, we have adjacent over hypotenuse for cosine, 1 over square root 26. I'm not going to worry about rationalizing that because I'm about to square it. So when we square it, we square the numerator and we square the denominator, no more radical. Then multiply 2 by 1/26 and you get 1/13. Minus 1 is minus 13/13. So it's looking like negative 12/13. Okay, now we have a series of, let's see, 1, 2, I guess just 2. I thought there were more. Maybe in the actual lesson there are more and they just didn't make it onto this slide. I don't know, you'll see if you go to class. So let's do these practice problems. And what you can do is pause the video, work them out, and then resume the video and see how you did. Okay, I'm going to work on the inside and find a reference triangle that represents the angle whose cosine is negative 1/3. And because it's negative, cosine is negative in quadrant 2. If I want, I can call that angle something. Maybe I call that angle theta. So I'm looking for the cosine of angle theta. And I know the adjacent is negative 1 and the hypotenuse is 3. Using the Pythagorean theorem, I get square root 8 for the other side. And I'm going to write square root 8 as 2 square root 2. Then I'm ready to find the tangent of that angle. And so to find the tangent of that angle, I'm going to use opposite over adjacent. And then to simplify that, we get negative 2 square root 2. Number 6. Here we have a more complicated inside, but this is an angle. We can call that angle alpha. And this is an angle, we could call that angle beta. So we're being asked to find the tangent of alpha plus beta. And according to our identity, that is going to be tangent alpha plus tangent beta over 1 minus tangent alpha times tangent beta. Okay, we need a reference triangle for alpha and a reference triangle for beta. So notice that alpha has a negative tangent value, so we're going to put that in quadrant 4. Negative 1 is the same as negative 1 over 1. And once you put those numbers in place, you might recognize this as a 45-degree angle. Probably doesn't matter. We can go ahead and put the hypotenuse value on there. And then let's also make a reference triangle for beta. Notice that 4/5 is positive, so we're going to be in quadrant 1. You can put 4 on the opposite, 5 on the hypotenuse, 3 on the adjacent, and you're ready to go. So alpha, beta. Okay, so now we need tangent alpha, negative 1, plus tangent beta, 4/3, over 1 minus negative 1 times 4/3. And now it just boils down to accurate simplifying. Okay, there's a variety of ways you could do this. One way that I like to use that works for lots of different problems is to start by simplifying the denominator. We have 1 plus 4/3. on the bottom. And on the top, we have -1 plus 4/3. Do not cancel the 4/3. Remember that. That would be incorrect order of operations. What I can do is I can multiply the top by 3 and the bottom by 3 to get rid of the fractions. Distribute. So 3 times -1 gives you -3. 3 times 4/3 gives you 4. And on the bottom, 3 times 1 gives you 3. And 3 times 4/3 gives you 4. So we have -3 plus 4 over 3 plus 4. So that gives us 1/7. That's not too bad of an answer. Okay, well, there we go. That takes us through the second lesson about inverse trig functions. Thank you for joining me. I hope you had a wonderful experience.